In record.
Oh, wow.
Okay, so welcome back. This is the last lecture of the day. It's by Andrew Macpherson, who is apparently shortly going to be here. And the title is Why Are Correspondences Ubiquitous?
Thanks for the introduction, Alan, and thanks for the organizers for inviting me or allowing me to speak. It's good to be back in the UK. I've been away for a while. Today's talk is based on work I've been doing in that's fundamentally a project of higher category theory. And, you know, I know this is a geometry audience, so I'm going to be nice and I'm going to keep it somewhat like a quasi-survey or overview of the subject and not really get into the meat of the category theory sort of Grothendieck constructions and Kahn fibrations that form the body of actual papers on the subject. I'm going to go over some examples and talk about what kind of thing the category theory of correspondences entails and quote a few results at the end without giving any idea of how such things are proved. So, of course, correspondences here is, I'm not talking about the plain English sense of correspondences. This is not that metaphysical. I'm talking about a category theory concept, which is a diagram like this. Everybody's used such diagrams before. A span or correspondence or a roof between X and Y in a category is a pair of maps from a common third object into the two objects. Often we consider the kernel, the central object W, to carry some additional information, which might be a function, a sheaf, a cycle, or some additional data. And this lives in some space. At the moment, I'm doing a sort of vague axiomatization of the system. It's contained in some space of coefficients attached to objects of the category, and this should have some functorial properties and a multiplication so that these things can be composed. And maybe I can no, we can use this eraser as a pointer. Yeah, so this sentence means that if my W is a kernel, I can, if I have a W equipped with some kernel, say a function, and I can push forward or integrate functions along certain maps, then I can just push forward this thing against the map from W to X times Y and consider it as a function on X times Y. If I can integrate along fibers. And so that's often a situation that happens, and we just think about correspondences between X and Y to be an object on the product. And the original diagram is a special case of this, where theta of W is just the slice category over W, the category of objects. This category here has the objects sort of pairs consisting of S in D, and S goes to Z. So plane spans without kernels is kind of a universal version of that. And we all know how to compose a sequence of spans with a common endpoint. We just take the fiber product of the kernels, and if there's a coefficient on the apex of the roof, you just take the product of them, tensor product of sheaves or product of functions. And so it's typical to arrange these things into a category whose objects are those of D and whose maps are the category of correspondences between X and Y. They're going to be objects, this category of things that look like that. And at this point, I am being a bit ambiguous about what kind of category this thing. Of course, if you want to be careful, you have to say, what kind of collection of objects is this? Naturally, it's at least a groupoid and not a set. So if we're trying to do things within the context of one category theory, you already exit that with this construction, because it doesn't really make sense to consider spans between X and Y as just a plain set. And of course, there's also a notion of map of spans, which means that there's non-invertible maps between maps in this category. So you end up with some kind of two category. So with that said, I'm going to just try and ignore that issue until later on when we pass to infinity categories and it all becomes kind of encompassed in the same framework. So I expect everybody's seen such things being used before. They're usually used to compare what I'm going to call linearizations of geometric or representation theoretic objects. So to manifolds or varieties, we look at the cohomology, which is a kind of linearization, or categorifying. We consider something like the derived categories. So these will be living in some, what I'm going to call a category of linear objects where it admits other constructions. So this is in, say, vector spaces. And then this is in, say, DG categories. It admits additional constructions to what you could do in the category of fields or varieties or manifolds. In the vector spaces, you can add, which is very convenient. That's not right. And in DG categories, you can do all kinds of things. One of the ones that's going to come up in this is adjoint functors. And in both settings, you've got a way of, usually got a way of going both ways. You've got going, given a map between objects in the original category, you can get mapped in both directions in the homology or the derived category. So that's what I mean by this two-way functoriality here. So I'm going to spend some time going over some of the examples I've seen and the kind of examples I think about when I think about this subject abstractly. So a very classical example is the Pontryagin duality between locally compact topological abelian groups. I should say abelian here. And in this case, there's a dual group, which is the category, is the group of maps, is the group of group homomorphisms between G and S1. So the character group of G. There's a famous Fourier transform of L2 functions on G, which generalizes the Fourier transform of functions on R or functions on S1 versus functions of Z versus Z index sequences. And I'm going to adopt, to fit everything into the framework of this talk, I'm going to call it, to say that this is defined by pulling the function back to G cross G hat and convolving it with, multiplying it with this kernel, which is a function of two variables, and then integrating out the G factor. So in other words, if this is P and this is Q, then F of P of theta is just integral over G's integral of the function P pullback of P. So times K. So it's a push-pull formula. And, you know, I could have put, it's just on the product here. There's no auxiliary third space, but auxiliary third spaces are still useful when you try to consider compositions of this with the Fourier inversion, which is then you end up with a formula, basically a function on G cross G cross G dual. So this function here is living on G cross G dual cross G, which is the fiber product of G cross G dual over G dual with G dual cross G. So it shows up in the composition of this thing with the Fourier inverse, which is given by a slightly different kernel. And the inversion formula tells you that those things give you delta, which is the identity, gives you the identity function when you convolve against it going from G to itself, which is what this map represents. So in other words, this is an equivalence. Well, we know it's an equivalence of the vector space of L2 functions, but it's already an equivalence in the category that comes before that, which is the category of groups where the maps, topological, locally compact topological abelian groups, where the maps are complex measures on the product, complex valued measures. I don't promise I've got all of the analytical subtleties right in this example, but this can be got right, and this is what it looks like. So this leads on to an example which is probably comes up more frequently in talks that people in this room attend, the Fourier Mukhair transform, obviously based because it's formality, named so because it's a formal similarity to the previous example. The relationship between an abelian variety and its dual is that they can, well, one of the relationships is that it can be, the derived categories of coherent sheaves can be related by pulling back, again, along here, and we get a map from DBA goes to DBA dual with E maps to Q star P tensor P star E, formula that everybody's seen a lot of times, I suppose. And again, of course, the way that you prove that this thing is an equivalence is you construct an inverse kernel. So this thing is an equivalence between A and its dual variety in the category of correspondences between projective varieties and equipped with a coherent sheaf on the product. And perhaps there should be a complex, an object of the derived category of coherent sheaves on the product so that it's closed under tensor products in the right way. And I've drawn up, I was going to say something else about this, but I've drawn a blank on it. Maybe I'll come back to that later. Here's another kind of example, also familiar to geometers. This one's not an isomorphism, but given a manifold with a Morse function and generic Riemannian metric, in other words, the context in which you can do simple finite dimensional Morse theory with isolated critical points, one constructs a family of moduli space or parameter spaces of Morse trajectories. So these are just all the, I'm not splitting them up by indices at this point. It's just the space of all strings of gradient flow lines for the gradient of f with respect to the Riemannian metric G. I've called these things parameter spaces because it's not traditional to formulate them in a way that an algebraic geometer would consider a modular space. One usually doesn't write of this thing. There has actually been some work in that direction by paper of Lurie and Tanaka doing this. Can't remember the year, I think it might have been 2019. Modular spaces of broken lines. So this thing has actually been constructed as a topological stack with a proper moduli functor. So I could have said modulo space here. So they fit into a correspondence, and these spaces are a disjoint union of spaces of a fixed Morse index. And so this object here, this Z tensor crit F, I just mean, you know, direct sum of crit F copies of Z is a graded abelian group. And there's a Morse differential obtained by pulling back to here and integrating against the fundamental class of the modulo spaces. And because this is just a number, not a form, this is only going to be non-zero of the fundamental class on the component where the fundamental class has degree 0, dimension 0, which is just the index 1 bit. So that's why this thing ends up being homogeneous at degree 1. And this is a fundamental. This is how you define the Morse complex. The point is that we're defining, the Morse complex is actually defined in the category of correspondences between sets whose kernel is a manifold with corners with an orientation on it. And more than that, there's an algebraic structure which gives you, there's an additional algebraic structure which you can also realize at the level of this correspondence, which is a part basically how you argue that b squared equals 0. So you've got some, here we've got a single object in some category of correspondences. Let me just correspondences between manifolds with corners whose objects are sets. And let's say oriented between crit F and crit F. You know, this thing is a category, and it's a monoidal category using composition of correspondences. So in fact, the full structure here is actually an object, an algebra object in this category. So this is what Morse theory gives you. And then final example is another step in the same direction. Pre-stable maps, as we will, this is the structure that defines quantum cohomology, which is the algebraic structure expressed by satisfied by Grover-Witten theory. So here we take, instead of the input is a complex projective manifold, and the objects are powers of that Cartesian powers of that manifold, and the kernels are moduli. So in this thing I've written is the moduli stacks of pre-stable maps from pre-stable curves into X, having a homology class beta. And the reason, so what I've written here is slightly incorrect actually. So I've written it with pre-stable maps. Yes, so basically if the sentence I wrote below is going to be true, I should have written this with the stable maps space. At least that's how it would normally be formulated. And this determines pushing and pulling against, integrating against the virtual class determines these orientations, which are components of the quantum product on X. The actual quantum product itself is a map from X squared to X to 1. But the reason to put pre-stable maps instead of stable maps is that we have these pasting identities, which is that M G I plus J times over X times over x to the j with, these are the frac m's. This is a boundary component of the space of glued curves. Which means that I think I need to put -1 in here. This means that you get an actual, the algebraic structure. Right. This means that the product structure exists at the level of these stacks. If you go to stable moduli spaces, then there's an additional stabilization procedure, which means that this algebraic structure will not actually define a cohomological field theory valued in correspondences. So this is a very sketchy example. I've omitted many of the details, but this was worked out. This perspective was worked out in the paper of Mann and Raballo in 2015. And they constructed sort of a higher derived categorical version of Gromov-Witten theory. Essentially, by this procedure, they first construct a what one would call a cohomological field theory, which is valued in the category whose objects are schemes and whose morphisms are correspondences, where the kernel is, well, it's a derived Artin stack which carries a virtual class by some derived stack magic. And then there's additional steps you can go through some additional steps with the stabilization and applying the derived categories to get to the ultimate object of interest. So once again, it was all defined at the level of correspondences. So the reason, so that was the examples. They're a little bit sketchy, perhaps, but this brings us to the question of trying to understand the common features between the examples, and that's where a bit of category theory comes in. So from now on, I'm going to start talking about correspondences in the abstract and how the properties of the category of correspondences, it already carries many of the properties that you might expect of categories of linearizations in the examples, vector spaces of functions, derived categories of sheaves. There's a graded abelian groups cohomology. These things we can add, and we can pull back and push forward, and we can take adjoints. And actually, we can do most of this stuff already in correspondences. So here's the setup. We're going to start with a finitely complete category. Again, I'm leaving the specification of what kind of category until a bit later. Of course, it's going to be an infinity category in the end. But it's already interesting when this is just a one category. And there's, I'm going to equip a set of maps stable on the pullback. So in examples, say if D is the category of schemes, typical examples for S would be something like proper maps or smooth maps or proper and smooth maps. Maps that, a class of maps that is going to allow you to have push forwards and base change formulas, which is something that's intrinsic to the subject. And this category of correspondences in D, this should depends on S, has the same objects as D, and the maps are spans. And the convention is that, for this talk at least, is that the wrong way maps are in S. And I'm going to denote maps in the category of correspondence in D with the dashed lines to distinguish them from those in D. And the composition in correspondences in D is the fiber product. So the first most obvious thing that you have is a functor from D, where you just have the identity, P be the identity map. The assumption would be that PS contains all isomorphisms. So certainly this is in the category, and this defines a functor from D to correspondences of D. It's not fully faithful because, of course, you have new maps. The whole point of it is you have new maps coming the other way, but it is fully faithful on isomorphisms. That's in classical category theory called a replete subcategory. It's also simply a categorical monomorphism. In other words, it's a monomorphism in the category of categories. So that's quite an important feature, is that the classification of objects of D doesn't change when you go to correspondences. You just get more ways to compare them. Here's the first linear feature of these things. Under some mild hypotheses, which are satisfied in all the examples that we mentioned, so manifold schemes, co-products in D become byproducts in correspondences of D. So a byproduct is just a product, is a direct sum. It's a product and it's a co-product in the category. And I've mentioned, I'll denote it with a, when talking about its the direct sum in core D, I'll just refer to it as with a direct sum symbol to emphasize the algebraic nature. And it's basically because the inclusion of X, you can just reverse it and consider it in as a correspondence in the opposite direction. So the mild hypotheses are that it's sometimes called extensive. It's not a very illuminating name. It's also basically it's that co-products are universal, meaning that you can pull back co-products. So yeah, I'll just write down the hypotheses because they're not very difficult. Co-products are stable for pullback. And then obviously you need a condition on S as well, because this is correspondences in D, comma S. And the condition you should have is that if X and X is in S, if this is in S and X primed is in S, then X disjoint union X primed is in S. So you'll see that that's true in the examples you can think of. So a category in which products are also co-products is called semi-additive. It's the main difference is, the only difference with it in an additive category is the lack of inverses to the sums. So in particular, you can get maps, you can get a sum operation in the mapping spaces. And the sum operation is just, it's given by disjoint union of the source. So let me just tell you what the operation is explicitly. So I should have a map from the n-fold product of core xy into core xy. And I'm just going to turn this into a correspondence between, not very clear. So if I have n correspondences between x and y, I can get a correspondence between n times x, so the disjoint union of n copies of x. And then I can just compose this. I can get this, reduce this to a correspondence from x to y by composing with the map n cross x goes to x. Compose. So just for free, I'm going to get an addition in this, and it's well, it's a homotopy commutative addition. It's addition that's modeled by the disjoint union of finite sets. And even if you started with a one category, you need to worry about this symmetry, non-trivial symmetry. In that case, it's captured by the notion of a symmetric monoidal structure on a one category, on a groupoid. And finally, the Cartesian, well, we have a Cartesian product in D because we assume that D is finitely complete, and this becomes some binary operation in called D, but it's not a product anymore. It's just something else. So we call it the, I write it as the tensor product symbol here to make sure it's clear that that's what, that we're not expecting categorical product property for this thing, although it does still come with its additional structure over a general symmetric monoidal structure, which is that it has its projections to the two factors. You know, we have maps x tensor y to y and x, which come from the projections in the original category. So it's still more than just a general symmetric monoidal structure. And finally, there's a duality story here, which is that if, so this picture should be familiar, might be familiar from the theory of smooth and proper DG categories in non-commutative geometry. If the diagonal or the projection to the point, this is the final object, is in S, then this span can be realized as a morphism either in one direction or the other from S. And this structure is what gives you this, like these two maps together define a duality on X with itself. So you end up with a self-dual structure on X. And this evokes the situation where if you have smooth and proper Calabi-Yau DG category, then you get a self-duality on that up to a shift, which is given by the dimension. So that's only used so far the, let's say, the notion of the infinity one category or the 2-1 category of spans. We didn't use any non-invertible maps to get all this. We already found there's addition on the mapping spaces, and there's a duality story, which can't possibly exist in, there's no way that you could have this duality already in D with respect to the Cartesian product, because there's no, only the point has a dual, you know, with respect to the Cartesian product. But there's more to say when you add non-invertible maps, and I will say it. So as well as the maps in D inducing maps in the same direction in core D, of course, maps in S, you induce a map in the opposite direction. And that's what I'm going to call F upper street. I'll call the ones in the same direction, of course. I didn't write this down. F lower shriek, which should be considered as this one. To be careful about making that menu appear. And in the one category story, there's only, that's it. It's just another map in the other direction. But in the two category, there's a relationship between them, which is that is the right adjoint. So you can see check for yourself that if I compose this span is representing the composite of F shriek composed with F low shriek, and the adjunction data. So this is a junction not between functors between categories, but just adjunctions in a general two category. The junction data is expressed by a unit and a co-unit, and it's just expressed sort of tautologically by this map. And it's, if you write down the composite in the opposite direction, you'll be able to guess immediately what the unit should be, and then it's just a sort of tedious exercise to write down the proof of the identities that they're supposed to satisfy, the triangle identities. And in fact, there's more than that. You can actually identify which morphisms are in D just from the properties, their properties as morphisms in the 2 category. Specifically, the if a morphism admits a left or a right adjoint in this category, then it is of this form. And I should just point out that the caveat that, of course, not all of these morphisms admit the F lower streak admit right adjoints, only the ones that are in S. And finally, there's one more thing that you can say about it. Forward and backward spans satisfy what people in category theory call the Beck-Chevalier condition. In algebraic geometry, we call it a base change formula. It just means that if for certain squares, specifically the squares where one of the correct map is in S and therefore the pullback is also in S, you can reverse 2 of the arrows and you still get a commuting square. So in general, if you have a square like this in the 2 category and these vertical maps have right adjoints, there's a way to get a comparison to cell between G lower shriek, F upper shriek, and F tilde upper shriek, G tilde lower shriek, and the commutativity of the square is saying that that particular cell is an equivalent. And finally, these squares that come from fiber products in D can be picked out again from the category of correspondences by this property. So all this together suggests that not only do categories of correspondences have these nice structures and properties that we get from we expect from algebraic natured categories, that actually they can be probably it's likely we can identify them among such categories as through these special ways we can identify the morphisms with left and right adjoints and the morphism and the squares that satisfy the base change formula. So for example, you can recover D as the left orthogonal. Yeah, another thing I didn't say is that of course every map factors if you have a correspondence from X to Y, then this is just going to be, this can be factored as the wrong way map from X to W and the right way map from X to Y. So in other words, it's just Q lower shriek composed with P upper shriek. So there's a factorization system into wrong way maps followed by right way maps. And this can be used to recover the maps in D as those in the other half of the factorization system to the ones admitting left adjoints, which are those in S. And I'm sorry about the alignment on some of these slides. It's just, I couldn't figure out how to get everything vertically centered in an easy way. So anyway, this is where it's living up at the top of the page. Basically, I'm going to move on to the results section now, but one future direction is that one can probably expect to be able to use the last comments I made. So about identifying the wrong way maps and right way maps and the Beck-Chevalier squares from the category to characterize categories of correspondences among abstract 2 categories. And this is going to be useful, I think, to for talking about generalizations like categories of correspondences equipped with a coefficient, which are actually necessary for getting to most of the interesting examples. And I'll give some more information about that in the next segment. So now I'm going to get onto some results. I wasn't claiming anything until now was rigorous, and from now on, I am claiming that it's rigorous. So the examples of this theory are all cohomology theories or derived categories. So we need to work in a homotopical setting, even if D is going to be just a classical one category, like the category of schemes. We want to consider theories valued in higher categories of chain complexes, spectra, or DG categories. So it's necessary to work in this context. In this context, the pseudo definition I gave for the category core D is not good enough as a definition to give a proper definition in homotopy theory. So this is not yet defined as far as this talk is concerned. So in classical category theory, we often say, oh, well, the objects are these things and the morphisms of these things, and then the composition is this, and obviously it's associative. We don't need to check that very carefully. Then that's as good as done. But here in higher category theory, we have to be a bit more careful. We have to either pick a model for higher categories and realize this thing carefully within the model. There'll be an infinite. The model will be some kind of an infinite structure, like a simplicial set. So there's an obvious way to define this as a simplicial category, as a twofold Siegel space. So we could define it as and in fact, it's quite kind of, if you look up the definition of twofold Siegel space, it's pretty obvious how you would define that. That's not the strategy I'm going to take for this talk. I'm going to talk, the other option you have other than describing an explicit model is to characterize it intrinsically, characterize it internally using the language of category theory. So that's the approach I'm going to take now. So from now on, you should not consider core D to be something that I've actually told you the definition of. And I suppress infinity from all the prefixes. Maybe this upsets some people, but it seems sort of just makes things a lot more convenient when you're working entirely in that world. So the context is I've said it a few times already. Now I'm not assuming D is finitely complete. That's a technical matter. I'm just going to assume that I've got pullbacks of elements of S. And spans are defined using this basic co-representing object, which is a free category on this graph. This here means that this map is labeled is an element of S, and this one is not. And a span in a category is just a functor from this thing. Is a marked span in a marked category is a functor from this thing into the marked category. So here I'm just defining the category of correspondences between two objects, not the category whose objects are correspondences and whose maps are, sorry, the category whose objects are, I said that in a very confusing way. The objects of this category are spans between X and Y. So these are the objects, and a map between two objects is just a map of spans, in the obvious sense. So this is a map in this category I'm defining. And perhaps this terminology would have been more obvious if I gave the notation in the definition. It's this thing. And the way I'm going to characterize correspondences is using this notion of bivariant functor. So bivariant functor is a functor into a two category, for example, category of categories, category of DG, compactly generated DG categories, such that everything in S admits a right adjoint, and such that the base change property is satisfied. So, typical examples where, base change is satisfied will be derived category of coherent sheaves, where you have a proper smooth map, base changes in Natal cohomology. This is the situation that this is abstracting. And then given a bivariant functor, one can construct a functor on for each individual x and y, you can construct an extension of this thing, which does the thing that it must do. It sends this chap to P. So here is what you might call Q lower star P upper star, but this is in K now. So really what I mean by this is just H of P. Sorry. This is the sort of right adjoint to H of P, and this is just H of Q. So it's the obvious thing that it has to be. And then using this, one can construct this is already enough to tell you what the category of correspondences is, and it allows you to construct, and this is the powerful part of the statement, functors out of that thing. Right, so the statement is that there is an infinity two category core D. I've given it the suggestive name of the thing I was talking about for the rest of the previous part of the talk, but in fact I'm defining it in this theorem, such that an inclusion of D into core D such that the restriction along J, that's what this map is. So the natural obvious map goes this way, and its restriction is just composition with J, and uses an equivalence between these functor categories. So in other words, this to infinity, this sort of infinity two category core D contains all of the maps that you can define in any in the image of any bivariant functor and valued in any category. It contains all of the sort of motivic maps between those objects. And what's more, this isn't a completely arbitrary infinity two category. It's an infinity two category which deserves to be called the category of correspondences. And in particular, its objects are just the objects of D. That's this statement here. And the canonical map, which I referred to in the previous slide, is an equivalence. So the categories of maps between two objects are indeed correspondences. And I didn't mention it in this, I didn't write it already, but one can also compare the composition law. Composition law is composition of correspondences. And status of this result is it's well, it appeared in a well-known book, Gates-Green-Rosenblum, Study in Derived Algebraic Geometry. It's this was based on some open, unproven, and as far as I know, still open hypotheses about the nature, about basic infinity two category theory. In my paper from last year, it came out in May last year, it's proved in a completely different style. It's more conceptual and uses, well, Gates-Green-Rosenblum used the Seagal space construction, and let me say that my approach was more using more internal logic of categories, which is what I've the way that I've expressed it in this theorem. And this was under a different hypothesis about basic infinity two category theory, which is basically the infinity two category Grothendieck construction. But then there seems to have been a lot of progress on this subject this year, and that's what this list of references at the bottom are. So I haven't quite looked into the details yet. There's probably some issue of comparing the exact definitions used in these things. But it looks like basically that this hypothesis is now pretty much resolved. So this can be subject to dotting T's and crossing I's. This can be considered an unconditional result. So this is right. So this is even telling you something new, even when D is just a one category, like the category of schemes. it tells you how in the image of some functor, like say the derived category, is telling you that the complete set of maps that can be constructed by pulling and pushing along correspondences and all the coherences between them can be drawn inside this geometrically defined category of correspondences. So that's a theorem. I'd like to move on to some more speculative stuff that's tying closer into the original cohomology story, which started this whole thing. So for that to work, I need to bring in the coefficient. Was there a question? No. So to be able to say anything about that, I need to bring in some kind of labeling on the maps or objects, which is like the kernels or coefficients I mentioned in the introductory slides. So for this, I'm going to use the concept of a labeling scheme on D. So I don't give a precise definition of this because at the moment the precise definition is it's contained in a paper of Manto, Hoiwa, and the complete list of authors is written on the next slide. The paper is called Motivic Infinite Loop Spaces. But basically, I want to start labeling my maps rather than the objects. The maps in one direction on the correspondences with some kind of orientation data, which is used to push forward cohomology classes. That's the intuition behind it. So for each element in the special set of maps, I'm going to have some set of coefficients, some set of orientations, if you like. And these have an algebraic structure, which is you can pull back orientations and you can also compose them. But of course, this isn't a very good definition of what I've written for, certainly it's not even good enough for one category, let alone for higher categories. One can formalize this using a Siegel space, which is what goes on in this paper. And I didn't want to write out the definition here because it's, a bit dry. So using this notion of correspondences with coefficients, and the examples of these will come in the results which I'll state below, or the conjectures which I state below. One constructs a correspondent category whose objects are those of D and whose maps are correspondences labeled with one of these elements of this labeling scheme. So a lot of the same categorical properties that you get for ordinary correspondences. So just to remind everybody that this implicit infinity convention means that I really mean, of course I mean infinity one category. You have a lot of the same properties again. You have you get the direct sums, you get the commutative, homotopy commutative monoid structure on mapping spaces. You get the factorization system, and you get the map from D into core times into these labeled correspondences, which is again a categorical monomorphism. So the classification of these objects doesn't change, but you have still more interesting maps between them than you did in the unlabeled correspondences part. However, in the actual examples where you, in the results we're about to state, there's going to be some destructive process done to this category here, which is going to change the classification potentially. So now onto the examples of this. So correspondences, of course, play a big feature in motives, and in fact, Grothendieck's original idea was to use correspondences like a cycle, a Chow cycle on the product to define Chow motives, and this idea has persisted in the theory till today, where more sophisticated versions are used to define fancy things like the motivic stable category, which is what this is about. Well, in fact, the motivic stable category is not usually defined this way, but this result of Elmanto, Khan, Sosnilo, and Jacobson shows that it can be defined this way. So the setup is K-schemes of finite type over a perfect field, and the wrong way maps are restricted to be flat LCI, and we will finite flat LCI. And we fix a framing on these maps in the wrong direction, which is just defined to be a K-theoretic trivialization of the cotangent complex. So the objects in this category core prime ds theta are smooth K-schemes, and the maps are correspondences whose kernel might be a non-smooth K-scheme, but which is a finite flat LCI over the source, and is decorated with this trivialization. So this is a kind of analogy to something that you might expect in ordinary theory of manifolds, which is that a framing on a manifold gives you a fundamental class in stable cohomotopy groups, stable homotopy groups. And this is the algebra geometric analog of that. So I called this a conjecture. Really, the statement in this paper is that the category of that a completion of this category does indeed embed into the stable homotopy category, the motivic stable homotopy category. And the reason that this is a conjecture is that it's not obvious that the localization of the subcategory is the localization of the ambient category. So it is true that if I take this thing and then localize it at the Nisnevich local A1 weak equivalences, then this thing does embed in the motivic stable category as the subset of a sort of what they call a very effective where very effective objects are basically just by definition the image of this. So that's kind of tautology that it's the very effective ones. But yes, there's a non-trivial statement that the maps in this category, in the category of motivic stable homotopy types, can be computed using these correspondences. So that's what correspondences give you here. And I'm just going to wrap. I've got 2 minutes left. I'll wrap up with an alternative differential geometric version of this conjecture for the theorem. There's a lot of words in the slide which I don't have time to explain fully, and which in any way are quite apart from the topic of the rest of the talk. But the point is that there's a category you can construct whose objects. So the idea is that using the methods which were used in the proof of the theorem on the previous slides, which the theorem of this paper, together with the which is all methods more similar to the ones used to prove the universal property results. One can study a category whose objects are smooth manifolds and whose maps are correspondences between two smooth manifolds, where this thing is a compact quasi-smooth derived manifold plus a tangential structure, and the tangential structure gives you a fundamental class inside Bordism theory. And there's the conjecture basically is a way of organizing. It's a statement about the Bordism classification of these derived manifolds with tangential structures, and how to organize them into a full category of correspondences. So although this theorem, I've tried to formulate this theorem so it looks formally very similar to the result in the previous slide, the main difference is that instead of localizing it, I'm going to enrich it and then take the homotopy type of the mapping stacks. But being differential geometric, the methods are probably totally different. And I have a pretty good idea of how this result is proved. And it's basically amounts to transposing classical arguments into a modern setting and applying the category theory of correspondences that I developed for the universal property back in theorem 5. So I'm now out of time, and that's the end of the talk. So thank you very much.
Does anybody have any questions? Any questions in chat or from people watching remotely? Okay, cool. Well, let's thank Andrew again. What time do we start in the morning, Miles? 10 again? We start at 10 a.m. tomorrow. See you all there. Have a good evening.